second block, but I didn't do that today.
Okay. So, number 1, is the speed of the particle increasing or decreasing at t equals 5.5? What'd you say?
Decreasing.
Decreasing. Okay. So, speed decreasing or increasing is the question, and we're saying that. Okay. Now, let's need to go out of that. Okay. You're saying decreasing? How did you get that?
Acceleration is zero.
Acceleration is negative. Chris, why are you shaking your head? You mean increasing?
Or acceleration is positive.
You said acceleration was positive. Why? I think I agree with the acceleration negative. Because don't you just take 5.5 and plug it into the acceleration equation?
Right here it says at x0
Yes.
2.
Right.
So I typed in the acceleration graph.
Right.
It was at like 0.27 at 0.
Oh, at 0. Okay.
So I had to move it up to because it's 2 at 0. Oh wait, I did that wrong.
Yeah, because that's not the acceleration graph, right?
No, I looked at it wrong.
Oh, okay.
It's exit.
Well, I did. Here's my question. Is acceleration negative mean that the velocity is, excuse me, yeah, darn it, see velocity. Did the question talk about velocity? Did the question ask about velocity? No, it asked about what? Speed. Those are two different, well, they're closely related, but they're different. Speed and velocity are different. Now, you guys are thinking of the chart, okay, and velocity and acceleration, I would agree. If acceleration is negative, that means the velocity is decreasing. So the answer to the question, is the velocity increasing or decreasing? The answer would be decreasing because the acceleration is negative. But it didn't ask about velocity, it asked about speed. Now what's the difference? Because if somebody said to you, my velocity is decreasing, wouldn't you think they're slowing down? Wouldn't that be the first thing to come to mind? Now, if you've been in physics, you may have a little bit of advantage on this. I don't know how much of this you've talked about. But if somebody says their velocity is decreasing, does that mean they're slowing down? No, it doesn't. Okay? Because remember, negative and decreasing, negative, number one, velocity has direction. And decreasing, and we talked about this early in the year, there's two different ways for numbers to decrease. They can be positive and get less positive, or negative and more negative. Now, let's look at it this way. Now, actually, I'm going to look at this two different ways. We'll look at it first from a mathematical kind of graphical way. Then we'll talk about it just from a physics way. Then they tie together and see how we can think about this question. So, if I was to give you a velocity graph. Okay, here's a velocity graph. And we'll say from 0 to, oh, let's say 6. And we'll call that 3 right there, just for the heck of it. Now, is it true to say the velocity is decreasing? Isn't that true? Right? The whole time, the velocity is decreasing. Now, here, the velocity is positive and getting less positive. Here, the velocity is negative and getting more negative. But either way, that's velocity is decreasing. Now let's talk about the object. Let's say the object's moving left and right. Right is positive, left is negative. So what's the object doing right through here? Going, since the velocity is positive, it's going to the right. But it's getting less positive means it's what? Slowing down. So this is right and slowing. So is its speed increasing or decreasing?
Decreasing.
Its speed is decreasing, it's slowing down. So right here, the velocity is decreasing and the speed is also decreasing. But right here, what's the velocity? Negative. So the particle's going where? Left. And its velocity is getting more negative. So it's doing what? Speeding up. So it's now going left and speeding up. So its speed is what? Increasing. Its velocity is decreasing, but its speed is increasing. Let's take the example of throwing a ball up in the air. Acceleration of gravity is what? Negative 9.8 meters per second squared. And that's because it's negative because it pulls, the force pulls in the downward direction. If I drop a ball, it's going down. The velocity is what when it goes down? Negative, right? The velocity is negative when it goes down. The acceleration is also negative. What's the ball do? Speeds up. But if I throw a ball up, it's got a positive velocity, but the acceleration is negative. What's the ball do? Slows down. So to tell if the ball is speeding up or slowing down, you need both velocity and acceleration. Both velocity and acceleration. So the physics way of looking at this would be, you would do A of, well, not just physics, but the math way too. You would do A of 5.5 and see that that comes out negative. So really, to solve this problem, here's what you would do on the AP test. You would plug with your calculator 5.5 into the acceleration equation and you get the negative. That doesn't tell you if it's speeding up or slowing down. Too many people confuse deceleration. You know, negative acceleration you think is deceleration. That's not true. Okay? Deceleration is slowing down. But negative acceleration could be speeding up. If I've got a ball that I drop and it's going down, it's got negative acceleration, but it's speeding up. Okay? So you have to also plug 5.5 into the velocity equation, and you get a negative. So what does that tell you about the object? Now this particular object's moving on the x-axis, so this is left or right. So what's this tell you? It's moving to the left. And the acceleration negative means the force is pushing it to the left. So therefore it's doing what? Speeding up. So the answer to this question is the speed is increasing. The speed is increasing because its velocity and acceleration are both negative. Now that's something we need to tuck away, and we need to know that for the rest of the year. You guys did a good job with the chart thing. If it would have been velocity increasing or decreasing, then we just look at the acceleration's negative, so velocity is decreasing. But speed is something different. Now, here's one other way we could have looked at this, and this is something else we're going to want to memorize and know. If I call S the speed equation, how does speed compare to velocity? So speed is always
Absolute value.
positive. Speed is the absolute value of velocity. Now, if we would remember that, that is going to come in handy in many, many applications for us this year. Speed is the absolute value of velocity. Now, one thing that also will help us then is, what do you do with an absolute value graph? What does it mean to do an absolute value graph? Well, since absolute value makes everything positive, if I was to do a speed graph here for this one and tell you that it should just be the absolute value of this graph, and if absolute value just makes all the negative positive, wouldn't this graph just look like this? Kind of like that? Right? I just took all the negative parts of the graph and flipped them up and made them positive. Now, it's easy to see, when is the speed increasing? We said here it was slowing down. Well, yep, speed's decreasing. Here it was speeding up. Yep, speed is increasing. See what I mean? So if we just take speed as the absolute value of velocity, take our velocity graph, turn it into a quick speed graph, we could have answered that question easily that way too, by drawing a graph of it. Matter of fact, that's true on any absolute value graph. If I ask you to graph this graph right here, okay, I think you should be able to graph that, or at least give a decent sketch of that by hand. Forget the absolute value bars for a second. Just look at the inside. What is that? Parabola. What happened to it? 3 to the 3 to the right, and down 4. Okay, I don't know where it crosses for sure. We can plot some points, find out. That's the inside. Then what does the absolute value do? right? So if you were to look, if you were to graph that on your calculator, you would get that graph right there. A cool looking graph, but that's what it would be. It would just be the parabola, and then all the negative parts would be flipped up to positive. So anytime you're asked to graph an absolute value graph, just graph what's inside of it, and then take anything that's negative and make it positive. Okay? But that works really well for this speed velocity thing. Just remember, speed is the absolute value of velocity. All right. So, kind of a long explanation for that question, but that's the first time we've kind of seen that thing. We'll go a little quicker here. Number 2. What'd you get for number 2? This should have been a really easy one. What do you got? Quick, quick. Huh?
-8/3.
Thank you. -8/3. What'd you do?
52 minus 60
Yeah.
divided by 5 minus 2.
Slope calculation. Is that easy? That's you got some points there. Took you 2 seconds. Okay, slope calculation. Number 3. Write the equation of tangent line. See this? Think this AP test is going to be hard? This isn't going to be hard. This is easy. What do we need to write the equation of a tangent line? We need the point at 1/2. Oh, gee, look, they gave us the point at 1/2. There it is. And we need what? How do you get the slope? Here it is right there. What's the derivative of that? 24x squared. Plug in a 1/2. You get what? 6. So there's your point. 6 is a slope. Write the equation of tangent line. Right? Slope, put in the slope, put in the point, and you got it. Well, that's easy. Geez, we're going to ace this thing. All right. 4 we skipped. 5 we did yesterday. Let's go to number 6. Okay, we have a piecewise function, and we are supposed to A, is f continuous? What do we do? Plug in a 0 into both of them. What are we hoping happens? Get the same output. If you've got a piecewise function and it's not continuous, it means there's a gap, there's a break. So this graph comes in at this y value and the other graph leaves at a different y value. But if this graph comes in at this y value and the other graph leaves from that same y value, now it's not broken. Now it's continuous. So it's that simple. So you put a 0 into here, sine of 0 is 0, we get 1. Put a 0 in here, e to the 0 is 1. There you go. I mean, you would want to show that work a little bit. You'd want to say, you know, show 1 minus 2 sine 0. This is no calculator, but so I would write that out. Show that that equals 1. Then e to the -4 times 0, that equals 1. Since they're the same, it is continuous. Okay, so that's not bad. Then it says, part B, for x not equal 0, express f prime as a piecewise function. What do we need to do there? Just do the derivative of each one. So f prime, so our piecewise function f prime equals this, boom. So the derivative of that, 1 is 0. This would be -2 cosine x. That's all you do with a piecewise function. Do the derivative of each of the pieces. Derivative of this would be what? Got to kick out -4, right? So you can see you've got to know the derivative rules because where we're about to go next today is chapter 4, and chapter 4 is applications of derivatives. It's, okay, now that we've learned about the derivatives and we know something about some things we can do, maxes, mins, chart stuff, what are some things that we could use derivatives for? So we're clearly going to have to be able to do these rules. Okay, so there's your piecewise function. Now, find when f prime equals -3. So I do what? Put -3 in where?
You have to set them both equal to -3.
Yeah, because I want to know when the output is equal to -3, right? So I have to set them each. So I have to do -2 cosine equals -3, and I have to do -4 e to the -4x equals -3, and I have to solve those. Now this is no calculator, so I divide here by -2. I get 3/2. When does cosine equal 3/2? Never, right? Cosine's always got to be between -1 and 1. So that rules out that part. And so over here, what do I do here? Well, divide by -4. This is all no calculator. Get 3/4. Now what?
ln of 3/4 is equal to negative 4x.
Log of both sides, log of, do ln of this side, will get negative 4x. I was just in Mrs. Andreessen's classroom yesterday, and they were doing logs. You guys probably remember that. Hopefully, you remember that. So at least I know you've seen it before. But you do the ln of both sides, you get this. Then we divide by negative 1/4, or excuse me, negative 4. I would write it this way, negative 1/4 ln 3/4. Okay? Now, you might be tempted to just leave that as your answer. And if you didn't even think another thing about it and you just left that as your answer, you'd be right. Somebody in the other class brought up the fact that, wait a minute, this is negative. And this piece of the graph is only for x being positive.
But ln of 3/4 is negative.
The key is ln of 3/4 positive or negative, right? I mean, it was a great question to ask, because I'm glad that they even realized to think about it. Because if you get an x value that's negative, we wouldn't count it here, because this graph only is for when x is positive. So we only want the positive x values there. Well, you have to know how, and they can do that too. You have to know what ln of 3/4 is. Well, the easiest way to know what ln of 3/4 is to remember the log graph, the ln graph. And I've told you this many times, and there are going to continue to be times where knowing what the ln graph is going to be helpful. It crosses at 1. So anything less than 1, like 3/4, you put that into ln, you're going to get a negative value. So negative 1/4 times ln 3/4 is a positive value. So there's the answer. Okay, so you can go ahead and hang on to that, and as we learn some more stuff, we will come back to this and we will do some more of those parts. All right, so the next thing you need to do is open up your book to page 212. While you're doing that, I'm going to pull up a couple of the calculus carols from last year and give you an idea of what a few people tried. Yes, for their extra credit last year. Yes. Oh. Thank you.
Well, I estimate.
Okay, Mr. Steele stopped in last year, evidently.
Didn't he say it was going to be recorded?
I did say it was going to be recorded, yes.
Do impressions, okay? But you know, I'm not Rich Little. I'm not somebody that does impressions as a rule. But this is an impression that I'm pretty good at, and I'll share it with you. This is my impression of a plumber opening his Christmas present. Okay, this is a plumber opening his Christmas present. Okay, there it goes. Wow, a wrench. Thank you.
Like I said, they don't have to be good.
Thank you.
They don't have to be good, because obviously that one wasn't.
Here comes Mr. Clark, here comes Mr. Clark, right down the math hall. Tablet to make this class less dull. Exponents and logarithms, always such a guess. Formulas ready, calculators on in Mr. Clark's calculus class. Here comes Mr. Clark, here comes Mr. Clark, right down the math hall. Trigonometric functions are dumb, make me feel so small. Must be time for another calc test. Soon on me, Mr. Clark, my mom is going to ball. Please tell me this stupid song will help my grade to pass. Oh my God, the humanity and Mr. Clark's calculus class.
Okay.
Here we go. Here's another one. You want to do a group one?
1, 2, 3. Trig functions, derivatives, and the chart. Calculus is hard, but it's really fun. Studying and working on our 89s. Asking like how to F to solve. Trig functions, derivatives, and the chart. Big F prime is the same as little f. The chain and product rules really help. On a gateway test, second block, it's the best time to get off track a bit. Discussing the solstice and the equinox, learning more about life through calc. If you know how fast, then you know how far. This is the speed limit law. Calculus is really beautiful. That's why calc, that's why calc, that's why calc rocks.
All right. So there's a couple examples. I'll pull up some others. I've got some from some previous years too that I don't have on my computer. So anyway, gives you some ideas. Okay. All right. And, you know, somebody, have you ever heard Adam Sandler's Hanukkah song? Yeah. Okay. That's one of my favorites in somebody did. They actually brought a guitar in and used that and played to that tune, and so that was good. And somebody, one group last year, I'll show you that one. That was Lily Munn and who else was in? Tony Munch. And I don't remember who else was in there. They did just poems, and they weren't even really Christmas poems. They were haikus or something. I don't know. So that'd be okay. So whatever. I mean, that. You want to have costumes? Nobody last year really did too much. But we've had people in costumes. We've had, like Jordan, you have your Christmas. You've already got your costume. We've had people bring in friends who were in orchestra and play the violins in the background or whatever. So, whatever. Now we've got a shortened period. I mean, we've got like 40 minutes that day, and but that'll be plenty of time, I'm sure. All right, page 212, if you would. Page 212, if you would.
Yeah.
All right. Now, chapter 4. Chapter 4 is, and matter of fact, let me just pass this out right now. Chapter 4 is applications of derivatives. So every section in chapter 4 is kind of different. I mean, they're not really related. The only thing that connects them is the fact that you use derivatives somehow in working them out. Okay? In other words, there's a section on finding max and mins, which we've already talked quite a bit about. There's a section like we're going to talk about today on differential equations. Those have derivatives in them. We're going to talk about tomorrow, or maybe Monday, it would probably be Monday, we're going to talk about some more limit problems. We're going to talk about ones that involve a derivative to help solve. So you can see that there's kind of a mixture. We kind of skip around here as we go through chapter 4. So each section kind of stands on its own. The only connection is that somehow it involves using derivatives. All right. Well, the first one we're going to do is differential equations. Okay? And the second one, section 2, that we start on Monday, will involve limits. So we've already talked about both of those things. We're going to just add to it a little bit. And then that's what that quiz, we're going to have one more quiz next week. So basically we have 3 more grades to go in the grade book. You've got the water juice extra credit. You've got your calculus Carol's extra credit. I take it back, there's 4. There's those 2 extra credit things. Then there's the quiz that we'll do next week, probably on Thursday. And then there's the one more homework grade to go in based on the homework that you've had up to this point. Okay, so those are the things that go in the grade book yet. All right, the first type of differential equation we had were the ones we can solve. Okay, like a y equals 3x plus 2. right? That kind of thing. Now that's y prime. Y prime equals 3x plus 2. Now what's a differential equation? What's a differential equation? An equation with derivatives in it, right? It's got an equal sign, it's got a derivative in it, it's a differential equation. Okay? What's the solution to a differential equation? The original function. If, in other words, we start with y prime, we want y. We start with f prime, we want f. That's what it is. Now, for this one, it's easy to solve. We just do an antiderivative. What would be the antiderivative of this? We haven't done those for a while, but 3 halves x squared plus 2x plus c. Remember that plus c, that was, you know, the unknown constant kind of thing. If I give you an initial condition called an initial value problem, we could plug it in, we could find the c. All right. The second type of differential equation was the memorized. Now, we had one that we memorized, y prime equals ky, and that solution was what? Y equals ae to the kt. It was exponential growth, and if you were doing an exponential growth kind of problem, you would use that to plug your values into. We're going to add one more today. Now, our homework's going to basically be two types of things. One of the things it's going to be is this new differential equation we're going to learn. And it's very closely connected. It's y prime equals k parentheses y minus capital T. Like that. Now that happens to be the same differential equation we did in that 2011 AP packet yesterday. Number 5 with the weights. If you remember that, it was 1/25 times W minus 300. T is a constant here. Capital T is a constant. K is a constant. Y is the output variable. The solution to that, we didn't know how to solve it at the time, but the solution to that is y equals capital T plus ae to the kt. That is our new differential equation that we are going to just know that the solution is that. It's basically the exponential function with a vertical shift, is what it is. All right, and then of course we had the third type, which we didn't know how to solve, and we could verify, but that's about all we could do with it. We could verify that it, you know, that something was a solution, do the T-chart business. Not going to be a lot of that on this next quiz, though. We did a quiz already where we had to verify solutions, do that kind of thing. Okay, we're gonna, you'll see that the new stuff we're adding to it here today. All right, so for your homework, there's going to be two types of things that I'm going to want you to be able to do. All right. One type of thing is this differential equation. Now, it does have a name. It's typically known as Newton's law of cooling. Now, remember, you may remember this differential equation. It was on our last quiz. Well, not the gateway, but the quiz before that. Remember the problem where I asked you if K was negative or positive, and you had to tell why? And we said that Y was the temperature of the coffee in the room, and right? And we talked about how K had to be negative because this would be positive because Y is the temperature of the coffee and it's greater than T, which was the room temperature. And since the temperature is decreasing, then we know Y prime has to be negative and this is positive, so therefore K has to be negative. Another thing that I want to mention about this differential equation, remember when we did the water tank, Torricelli's law, the water draining out, and we said it goes faster at the beginning because that's when Y is bigger, there's more water in the tank, so the rate would be bigger then. Well, same thing is true here. When's this going to cool the fastest? At the beginning. Because at the beginning, Y is the biggest. T stays constant. But the temperature of the coffee is the biggest. So the difference, what this represents here is the difference between the coffee's temperature and the room temperature. And the greater that difference, the faster it'll cool. As the coffee gets closer to room temperature, it slows down how much it cools. It makes sense that that would be an exponential function. Now remember, we said K is negative. So an exponential function with the K negative actually is a decay, kind of goes like that. And it's going to be shifted up T units, which is the room temperature. Doesn't it make sense that the coffee would cool faster in the beginning, then it would level off, and it would level off right about room temperature? So it's an exponential shifted up T units. That's Newton's law of cooling. So one thing you will have on the homework is you'll have some problems. For example, it'll sound like this. You'll have a cup of coffee started at 200 degrees in a 70-degree room. Well, That would mean you'd put a 70 right there. You'd put a 0 in for t, little t is a time. You'd put a 200 there for y, right? And that would help you find a. Then 4 minutes later, it cooled down to 180 degrees. So you come back and you put a 4 in for t. You already know this is 70. You just found a. Now you can find k. Now that you know big T, you know A, you know K, now you know the equation for the coffee. Then it'll say, how hot was the coffee 10 minutes later? Put a 10 in for T, find the temperature of coffee. So it's very much like problems we've done before. They give you some conditions, some numbers to plug in. You plug them in, you solve, you work it through, and you answer the question. Okay, so that'll be a couple of the questions on the homework. We'll be using Newton's law of cooling using this equation. All right. The new thing that we're learning today is this idea of slope fields. Slope fields. Okay? Slope fields. Now, when we solve a differential equation, we find the initial function, the original function. So that means we're going from like f prime to f or y prime to y. Well, I just reminded you how we did that with equations, right? You got y prime, we can do an antiderivative. Now, unfortunately, that doesn't work for some of these. But for these, it does. And we get that plus c. But remember back to chapter 1. And you don't have to write this one, this part down if you don't want to. It's up to you. But if I gave you an f prime graph, and I told you, you know, this is 1 here, and this is 2, and this is 3, okay, and this is -1 back here, okay, whatever. And I gave you an f prime graph like that. And I ask you to draw the f graph. Am I still on the screen? Okay. Just stay down here. You remember doing these? Here's an f prime graph, you draw the f graph. It worked in a sense we solving a differential equation there. We were going from f prime to f, the original function. So in a sense, we were graphically solving a differential equation. Okay? And that's what slope fields are. Is a graphical solution to a differential equation. So let's just review what we did for this. So we would look at f prime and we'd say, what's going on right here? What would we say about f prime right there? Positive and getting less positive, right? So what's my graph over here doing? It's going up because this graph, these are positive, and it's concave down. The slopes are positive but getting less positive. Now, where do I draw it? We don't know, right? That's that plus C part. That's that vertical shift part, right? We don't know. So we can draw it anywhere. So I'll just start here, and I'll draw it up, but it's decreasing. Until where? Until 1. And at 1, we have a local max, right? Changes from positive to negative. Now f prime is negative and getting more negative until 2. What's that mean this graph's doing? Doing what? Decreasing and concave down until 2. Now the slopes are negative but getting less negative. So it's still going down. So it switched to concave up. There was an inflection point there. Negative and getting less negative. These slopes are negative and getting less negative. And then we got positive and more positive, and it comes back up, and that's what we did. Now, we didn't know where it was, but that was our kind of our shift. Okay? Now, that's pretty rough. I mean, that's a pretty rough sketch of the solution, because all I did was say, well, it's going up, but it's concave down. But I didn't know how steeply it was going up, right? I just kind of guessed. I just drew it. So it's a very rough sketch. So what a slope field is an attempt to make a little more accurate sketch of that idea. So here's what it is. Instead of just looking at this, let's say this is a 2 right here, and this is a 1 right here. Instead of looking at this point and just saying it's positive, I'm going to look at that point and say it's a slope of 2. So I know at -1, my graph has to have a slope of 2. Now, I don't know where to start it, right? So what I do is at -1, I go in and I draw little slope segments like this that look like they have a slope of 2. You with me? So at -1, from my f prime graph, I can tell I have a slope of 2. Now at 0 here, it looks like I have a slope of what? What's that look like? Now wait, now remember, I didn't say it very well. I'm talking about f prime value. Right here I have an f prime value of what? About 1/2. So that means on this graph at 0, I need to have slopes that are about 1/2. So that means they would be less than those other slopes I drew, right? So I'm drawing in these tiny slope segments that have slope that are about 1/2. Okay? Now what about here at 1? 0. So at 1, I know my graph is going to have a slope of 0. See what I'm doing? I'm drawing in these little slope segments based on my f prime, because all I was given was f prime, which tells me slope. So I'm using that to draw these little, we call slope segments. So down here, let's say this was -1. So that means when we get over here to 2, we're going to have a slope of -1. So I draw in these little slope segments and so forth and so on. Once you get, and now if you look on page 212, right, look at those pictures on page 212, you can kind of see what we're talking about here. Okay? So when I'm done, what I have is called a slope field. A slope field. Now all we need is an initial condition, and then we just go with the flow through the slope field and we can draw our solution curve. And it would be more accurate because the slope field tells us about how much to go up and down and so forth. So if I gave you this f prime and I also said, okay, f of 0 equals 0. I said, okay, here's your f prime graph and f of 0 equals 0. Well, that would tell me I got to start here. So I would just kind of go with the flow and go like this, and and then I would go up, and then I would see that going back down, and when that just goes down like so, and there would be my solution. That is a slope field. We start with the differential equation, and we do this. Now, instead of doing it with graphs, we're going to do it with actual differential equations. So let's take one here. Let's take this one right here. Y prime equals 2t minus 5. T is going to be my input. Okay? So, we want to draw our slope field. So this would be labeled y right here. Okay? So we're going to just plug some numbers in. It's kind of like back in algebra class when you used to just plot points to draw a graph. This time we're plotting slopes instead of plotting points. So put a 0 in for t. What do you get? So that means when t is 0, I'm going to have a slope. That's a really steep slope of -5. So I'm just going to put in some slope segments like this. -5. Okay, let's jump over here a little bit. Let's jump over to 2. Put a 2 in. What do you get? -1. Okay, so let's draw in some slopes that would look like they're about -1. Okay? Let's put in a 4. What do we get? 3, positive. So that would be, they'd be a little steeper. Something like that. Now, you can see how this would take quite a while by hand to draw the pictures like what's in the book. Tomorrow we'll do an activity on our calculators where the calculator can do slope fields for us. Okay? But this gives us a general shape of what this is. Now, look at this. This is one we know how to solve. What would be the solution to this? This is an antiderivative one, right? Since it's got just the t in it. What would this be? T squared minus 5t plus 8. It'd be a parabola, right? We would expect our y equation to be a parabola. But we didn't have to know that. But looking at the slope field, you know what? If we plotted some more of it. Now this one actually is in your book. It's the bottom left picture on page 212. See that slope field? See, without those, pretend those blue lines aren't in there. Pretend the blue parabolas aren't in there. You could literally see the parabola in that slope field. What the blue graphs are just some different initial conditions. You get some different initial conditions, you could go with the flow of the slope field and just draw in your parabola. Okay? So it's a way of solving. So even if we didn't know how to solve the differential equation, we could plot points. That's what this amounts to. Plotting points, plotting the slopes, drawing the slope field. Now, you're never going to have to plot this many. If you look up on page 213, see that picture there? On the AP test last year, that packet we just worked on, there was not a slope field question. I bet there will be this year. Seems like about every other year. And it will usually look something like that. They give you a bunch of dots, maybe 10 of them or so, and then you have to plot points and you have to sketch a slope field. And it might look a lot like that one right there. Okay, so you usually just get a small piece of the slope field you have to plot by hand. Tomorrow we're going to also do an activity where we plot a few by hand. Okay? All right. So that's that one right there. Now, one thing I want you to notice about this slope field, because I told you there were two things you have to do on your homework today. Okay? One thing was the Newton's Law of Cooling business. The second thing is you have to be able to identify some slope fields. Okay? You're not going to have to draw them, but you're going to recognize them. And this is the key to recognizing them. First of all, a slope field like this, notice, this one only involves the input variable. Okay, we're just about done here. Then I'm going to give you some work time on this. Okay? This only involves the input variable. Now, why is that important? Because we know some differential equations have the input variable, some have the output variable, some have both, right? Okay? What you notice is, like here at 2, the slopes are all the way up vertically. The slopes are the same. Because that means every time you put a new input in, you get a new slope. So every time I move over to a new input, I'll get a new slope. And it'll be that same slope all the way up and down for that input. Okay? You'll see what I mean here in a second. Now let's do this one. Y prime equals y. Now we're not going to draw a slope field for this one because it's in your book. But this one only involves the output variable. Now, that differential equation is up at the top of page 212. Tell me what you notice. Now, forget the blue lines in there. Forget the blue curves in there. Those don't, just ignore those. What do you notice about the little slope pieces? If you go up and down, they change, right? But go across horizontally, they're the same, right? That's because the slope, remember, y prime is a slope. The slope changes whenever y changes. So whenever you go up to a new y, you get a new slope. Go up to another new y, get a new slope. Go down to a different y, get a new slope. So if the slopes stay consistent across, you know that the differential equation only has y in it. If the slopes stay consistent going up and down, you know it only has x in it. And then the last or the third slope field there is this one. Y prime equals y plus t. This one involves both t and y. Well, that means every time you change your input or your output, you get a new slope. So if you look at that slope field, if you go across, the slopes change. If you go up and down, the slopes change. All right. This is an important idea because one of the things you're going to have to do is match a differential equation with its slope field. And this can be one thing that can greatly eliminate different choices. All right? Let me show you in your homework here, and then we'll do one other homework question together, and then I'm going to give you the last half hour to work on your homework. Okay? So look at number 7. This is on page 217. Now, for right now, we're going to ignore those blue dots. Those blue dots are just some initial conditions. And the directions say to sketch the solution curves in there. You probably look in your book. Somebody's probably already done it. You're not going to have to do that. We'll do that on an activity we do tomorrow. Okay? So you don't have to do that part. All you have to do is the matching. Now, the 10 Roman numeral to the bottom left on page 217 are what you're matching these with. Okay, so number 7, that picture, and we're looking down at the 10 differential equations on the bottom of the page. What do you notice about that differential equation as far as those, I mean, that graph as far as those slope segments? They're the same thing going across horizontally, right? If you just run your finger across horizontally, the slopes never change. What's that mean? It's got just y in it. That's what it means, is it's got just y in it. So you go down to those choices and you can eliminate all the ones that don't have just y. Now, how do you choose between the ones that have just y? What's that? Yes, well, but you got to be careful, because remember, just because it says cosine y doesn't mean that it's a cosine graph. You see what I'm saying? Because that's the y prime equation, not the y equation. Always keep in mind, this is a linear equation, but that's the y prime. Our slope field was a parabola, because the slope field is the original function, right? Always keep that in mind, that when we get a differential equation like this and we draw these slope segments, these are the slopes of f. So this graph we're looking at is the shape of f, or of y. But how about plot points? Plot points, like take an easy point. Put a 0 in for y, which would be on the x-axis. Here, when you look at the x-axis, it looks like the slopes are about 1 or so. If you go down to Roman numeral 7, put a 0 in for y, cosine of 0 is 1. Except if you go down to 9 and put a 0 in for y, you also get 1. So that didn't work. That didn't eliminate those two. It does eliminate the last one. If you put a 0 in to the last one, Roman number 10, you get 0. Well, clearly number 7 doesn't have a slope of 0 when y is 0. So you can eliminate that one. So you have to pick a new point, pick another point, pick another y somewhere else, and then see which one it is. Okay? And that's how you're going to match these up. Okay? So you're going to have some problems. It's Newton's law of cooling. You're going to have some. You're going to have this set of matching. Now, if you look at the homework, I believe it says. We're going to do one of these together. I think it says 3 through 14. Is that right? On that sheet I gave you. Okay, and then 23 and 24. All right. So let's take a look at these. 23 and 24, that Newton's law of cooling problems. 7 through 14 is the matching. So, and 3 through 6 are all kind of the same. Let's do number 3 together. Then I'll give you some work time. Okay? Because one of the key aspects of slope fields is plugging into a differential equation. Plugging values into a differential equation to get the slope out. So you can draw the slope field or check the slope field or something. All right, number 3 says, suppose that f is a solution of this differential equation. You can call it y if you want. They call it f. You could call it y because they use that in the differential equation. And those are interchangeable. That's fine. And they tell you f of 1 is 2. Explain why y equals 3t minus 1 is an equation of the tangent line at the point 1, 2. Now, I think that's a weird way to ask that question. Explain why that's a tangent line. I think the easiest way to do that problem, to explain it, is to what? Just find the equation of the tangent line. Go through what we normally do. Just find the equation of the tangent line and show that that's what you end up getting. So, to get the equation of the tangent line, we need a point and? So we need f prime of 1. How do we get f prime of 1? Plug it into the differential equation, right? In other words, we're finding y prime. So you go to the differential equation, which is y prime. Oh, it's got t's in it. Okay, we'll put a 1 in for the t, but it's got a y in it. What do we put in for the y? We put in the 2, right? When you plug in a differential equation, sometimes you have to plug in the y, sometimes you have to plug in the x or the t, sometimes you have to plug in both. So we would plug in a 1 for the t squared times y, which is 2, plus, what is it? T, which is 1. And that would be 2 plus 1, that would be 3. So the equation of our tangent line is y equals 3, quantity, t, we got to use t now instead of x in this problem. T minus 1 plus 2. So y equals 3t minus 3 plus 2. Y equals 3t minus 1. There you go. So that just showed why that's our tangent line. Right? Easy. That's what we've done before with tangent lines. But they just ask those in a weird way. I mean, I think on the next one it says the same thing. Next one it says find the equation tangent line. Okay, fine. Essentially do the same stuff. Okay? That's your homework for tomorrow. And also, if you need to take another gateway test, study for that. All right, I'll give you the rest of the time to work on those problems.